Coordination chemistry, nomenclature, coordination chemistry. The reason why, like I said, I enjoy this chapter is because I did a lot of graduate work with this specific chemical right here. Mine was a slight variation, but I certainly used this chemical right there. That's called a ligand. Okay, you will be introduced to that terminology in this chapter. Ligand, some people pronounce it ligand. I was introduced as ligand. So ethylene diamine, for those of you who did experiment number 6, that's a ligand. Okay, anything that's bonded to a transition metal is a ligand. Anything that has lone pairs to donate to a transition metal, that's a ligand. So that complex that you see right there is actually a complex that I worked with in graduate school, and the idea was to these things absorb light really well. You shine light on it, they absorb light, and then um, what happens is that they go to their excited states, and then they relax back down to their ground state. But in the process of relaxing back down to their ground state, they shoot off radiation, and the chemical I was dealing with was very bright green, and we call it top green just because when we did chromatography on it, it would always be the top layer in a chromatography separation, and if we shine ultraviolet light on it, it would glow green. Okay, now why were we studying this? We're studying this because we thought we could make something called a photocatalyst. A photocatalyst is a chemical that would absorb radiation, probably radiation from the sun, hold it, and then transfer that energy to a chemical like water, and then use that energy to split water so you can get hydrogen. That was, of course, the end goal. Okay, the chalice of this research was to split water using chemicals that might do that. Of course, we encountered these chemicals. They were really amazing, but they were far short of what we wanted to do with water. Then the Japanese came around and realized that these things really glow really well, and that you can fine tune it by changing these ligands to different colors. And then they decided to put it in, not run sunlight or light through it, but electricity. And if you run electricity, you have a constant source of energy. And then they were able to figure out the technology so that they could make light or organic light emitting diodes. Organic light emitting diodes, OLEDs, are now what's in your iPhones or your Samsung or your TV. That has revolutionized the screen so that you can get brilliant color. But as they said, the people who discovered the chemicals generally don't make the money who discover these chemicals. It's the people who can figure out a way to the technology that could utilize it in the economy. Anyway, that's my story in terms of why this topic is near and dear to my heart. So let's look at some review. Some things that you need to know, and we are concentrating on transition metals here, okay, because transition metals has d orbitals. And as long as they have d orbitals, then they can accept electrons and bind an atom or groups of atoms called ligands. So you need to understand that transition metals have what we call different ways of giving up electrons. Some will give up one, some will give up, well, actually, this is the only atom that gives up one electron. Most will give up 2 electrons, some 3. One will give up 7 electrons. That's manganese. Why is that important? Because the electrons that they give up allows you to figure out how many electrons are left in the d orbital. And the number of electrons left in the d orbital will give rise to a concept called crystal field theory. Okay, so you guys should know how to figure out how many d electrons an ion, a transition metal ions, will have after it's given up uh, 2, 3, or 4 electrons. And that's an important skill that you guys already know. Okay, remember that as you give up 2 electrons, then its oxidation state is +2. If it gives up 4 electrons, then its oxidation state is +4. So oxidation state generally is the charge of that element as it accepts or gains electrons. Now, let me just show you the different properties of transition metals. And let me just show you this right here. And let's see. So this is a movie that let's see.
Bonding situations by observing the distances between atoms in.
Let me repeat this, okay, because I'm trying to coordinate the.
It is possible to estimate the radii of atoms in characteristic bonding situations by observing the distances between atoms in molecules. In any given group of the periodic table, for example, group 6A, the atomic radius increases as we move downward. As we move from left to right in any row, the atomic radius generally tends towards smaller values. This occurs because the effective nuclear charge acting on the outermost electrons is increasing. As we proceed across the first long row of the table, in which electrons are being added to the valence shell d orbitals of the metals, we see an overall decrease in radius as a result of increasing effective nuclear charge.
So that was just a preview of what you guys hopefully learned
estimate the radii of atoms
on what you guys should have learned when you did periodic trends back in general chemistry. Remember that this portion of the atoms are the smallest, or in the periodic table, this is the largest. And it has to do with the fact that as you go down the periodic table, you're increasing the shell in which the electrons lie, the valence shell, and therefore the radius increase. As we go across, what you're doing is you're keeping the valence electrons within the same shell, but you're increasing the number of protons. So we could have something called Z effective. Hopefully you guys remember about Z effective. It's the effective nuclear charge that the valence electrons observe in the nucleus after the shielding effects of the inner electrons. And because the outer valence electrons are responsible for the size of the atom, the greater that Z nuclear charge, the more attraction it'll have for the valence electrons, thereby collapsing the electron cloud and making those atoms smaller. And that's why you see that trend going across the periodic table. Now, this is all important because we're going to be using these properties to understand why the chemistry occurs, what type of chemistry occurs when we start having transition metal compounds. So here you can see the trend in terms of the atomic size. They generally go down as we march across, and then they go up slightly. And that's because, remember, when you fill the d orbitals, you go d1, d2, d3, d4, d5, and then d6, d7. Now you have 2 electrons in the same orbital, and you have electron-electron repulsion. And so that will expand the electron cloud slightly because you have electron-electron repulsion, and that tends to expand the electron cloud. Now, that's why you see this trend right here where it goes down and then it goes slightly up. And then if you go down the periodic table, this is the first row transition metal right here. Okay, let me change my, this is the first row transition metal. Then in here, there's second row transition metal, and then the third row. And you notice that the second and third row transition metal atomic radius are nearly identical. And the reason why that's the case is because something called the lanthanide series. Um, and in order to appreciate that, you need to look at the periodic table right here. And if you take a look at, this is the first row transition metal, this is the second row, and then this is the third row. But if you go from strontium to yttrium or barium to lanthanum, you have to go to the lanthanide series that are below the periodic table. And what you see is that you have to put in 14 electrons as you jump from strontium to yttrium or barium to lanthanum. And so what happens is that you put in 14 electrons, but that also means that you put in 14 protons. The 14 protons, as you jump from barium to lanthanum, will have a greater effective nuclear charge pulling in those valence electrons. And so the results that you see is that the second and third row transition metals are nearly identical in size, because these elements are going to have extra electrons that pull the electron cloud tighter. Okay, actually not so much the second, but the third row, the lanthanum series pulls the electrons closer and then collapse the electron cloud. So it's called the lanthanum contraction. Okay, lanthanum contraction. And if you forgot about this in your general chemistry part 1 course, then you guys could easily look it up. Here's an important table in that it's showing you the electron configuration for the transition metals. Okay, and the reason why this is important is because what will happen when electrons are removed from transition metals, they always come from the electrons that extend furthest away. Okay, and the electrons that extend furthest away are the ones in which the principal quantum number is the highest. So scandium has an electron configuration of, I believe it's argon 4s2 3d1. That's it right here, scandium. Let me clear this. So you guys should remember how to cite your electron configuration. But scandium has an electron configuration of argon that represents 36 electrons. Okay, and then we're in the fourth shell, 4s2. We're looking at 2 electrons here, and then 3d1. When scandium is ionized, it generally removes its 2 electrons from the s orbital. So it's got 1 electron, sorry, it removes its 2 electrons from the s orbital. So it's got 1 electron in the d. So we call scandium plus 2 a D1 species. Okay, we call it a D1 because the electrons that is lost is from the s orbital. Let's say we have iron plus 3. Well, plus 3 means that there are 3 electrons removed. The best way to figure out how many d electrons there are is just count 1, 2, 3, 4, 5, 6, 7, 8. There should be 8 regularly, 2 in the s, and then 6 on the d. But 8 minus 3 is going to be 5. It's a d5. Okay, it's that easy. Don't make it more complicated than it is. What you need to do is figure out how many electrons in the d orbital. Let's say I have iridium plus 3. How many electrons in the d orbital? Well, count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 3 is 6. It's a d6. Okay, that's the most efficient way of counting electrons in the d orbital. And I would recommend that rather than going in, and you could easily have done this as well, which I think is too much work. You can say, okay, iridium has the electron configuration of xenon, and then we have 6s2, and then it's got a, oops, sorry, 4f14, 5d, 1, 2, 3, 4, 5, 6, 7, 7. But in terms of the electrons, after it removes 3, it's going to remove this and this. So that's a total of 3. This thing will drop to a d6. Just like we did when I was showing you that simplistic way of counting electrons. Count 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 3 because it's a plus 3. That means it's losing 3 electrons. It's 6, it's a d6. Okay, so don't make it harder than that. If you do, well, it's up to you, but it's not that complicated.
Professor?
Yes.
So the d orbital always steals from the s in those cases?
The d orbitals are always going to be retained. The electrons in the d orbitals are always going to be retained before the s. The s are going to be removed first because look at where the s lies. In the fourth period, the d orbitals lies in the third shell. The s electrons lie in the fourth. And if you remember quantum mechanics, the electrons, the reason why they fill the s orbital first is because those electrons in the s orbital can penetrate to the nucleus, so they're much more stable. But at the same time, they extend furthest out from the nucleus because it's in the fourth shell, which means that they can be ionized or removed with much more lower energy than the electrons in the d. Okay, so whenever you're removing electrons, because you're ionizing the transition metals, pull them out from the s orbitals first. And then when you're forced to, then pull them out from the d. Okay, you guys don't have to worry too much about the lanthanide or the actinide. That's not crystal field theory. It's mostly concentrated on transition metals. Does that answer your question?
Yes, thank you very much.
Okay. Yeah, I'm glad you're one of the few that actually are not afraid to unmute yourself and ask the questions. And everyone should do that. That way, I don't skip over your chat comments because I'm generally looking at my notes, and every once in a while I'll glance at the chat. Anyway, that's important. Why? Because when we start looking at why different chemicals have different colors, you're going to see how important it is to count d electrons. When we start talking about magnetism, how many unpaired electrons, you need to be able to count how many electrons in the d orbital. If we were trying to figure out exactly what type of structure these things will have, it's the d electrons that are responsible for that. Remember what I said in the beginning of this course? We're looking at how atoms or clusters of atoms come together. And when they come together, it's the valence electrons that make first contact that is responsible for the chemistry that occurs. And so that's not so different as we look at specific examples in coordination chemistry. Now, a little bit of more review. When we talk about acids and bases, we talked about proton donors and proton acceptors, but we could also look at the flip side and say that acids are electron acceptors and base are electron donors. So that's the flip side of acid-base chemistry. And in coordination chemistry, that's very important because the metals are going to be your Lewis acids. They're going to have the d orbitals that are empty, that are available to accept lone pairs from the ligands. The ligands, however, will need lone pairs to donate to the metal, and so they are going to be the Lewis base. Okay, once they form a bond with the metal, then we have something called a coordination. That's why it's called coordination chemistry, because the two electrons that are coming from the base is actually not provided from the metal and the ligand. It's actually coming directly from the ligand. Okay, um, so ligands are the ones that are going to be bonded to the metal, and they could be atom or clusters of atoms with lone pairs. They have to have lone pairs. Okay, and some of these things, some of these ligands could be water, just like you saw in experiment 6, where water were bonded to nickel, and these things could easily be removed. Or they could be like water, remember, has two lone pairs that could donate to a metal. Or ammonia. Ammonia has one lone pair that it can donate to a metal. So these things could be ligands. Or the transition metals, because the transition metals, their ions have four lone pairs that they can donate to a metal. So these things are ligands, and when they bind, it's called a complexation. Remember Kf? We talked about that in equilibrium. Well, Kf is based on the complexation of ligands to a transition metal. So going back a little bit further, you guys remember about orbitals and the different types of d orbitals. And there were 5 types of d orbitals, and the 5 variable different types of d orbitals has to do with how they're oriented in space. If it's along the z-axis, like this, with a donut in the center, then it's a dz squared. When it's along the, this is coming out of the plane of my pad. If this is x and this is y, and it's along the x-axis and the y-axis, then it's a dx squared minus y squared. If they point, if this is x and this is z and this is y, if they point in between the axis like this, then this is, see how this is between the x and the z axis? It's called dxz orbital. So we have 5 of these. Let me clear this so that I can show you better pictures. Okay. You'll see that later on. But these are the sites where the ligands, the lone pairs, are going to be binding to. So it's going to be a Lewis acid, Lewis base type of chemistry. And here's an example of water with its lone pairs. And it is just going to donate it into the orbitals. Doesn't matter which orbital, well, it does. And later on, we're going to see which orbitals are going to be accepting these lone pairs. And depending on which orbitals accept the lone pairs, you're going to have a specific geometry, okay? So here's, this thing is called an octahedral geometry. And the geometry is always based on the geometry around the central atom. In this particular case, the central atom is the transition metal. And if you look at that right there, what you will have is bonds up and down. And then in this square-like arrangement, you have a bond that goes back here, a bond that go back here, and bonds that go out here. And the reason why it's called octahedral is because if you connect all of these, okay, what you will have is eight faces. 1, 2 in the back, 3, 4, 4 on top and 4 on the bottom. The 8 faces gives you the octa prefix. It's an octahedral geometry. Okay, so this is an example of an octahedral geometry compound, and the ligands that are directly bonded to that metal is within something called the coordination sphere. These are all the coordination sphere elements because they have direct linkage to the transition metals through bonds. Now, there's going to be, like in this particular example right here, the NH3, which is called an amine, is directly bonded to the cobalt, but because cobalt is +3, it's got to have a counter ion that makes it neutral. And so the chlorides, and there's 3 of them, that's why you see a 3 right there, are the counter ions that makes that whole chemical neutral. Ammonia is a neutral ligand. It doesn't bear a charge, but the cobalt, because it's lost 3 electrons, is a +3. And in order to make a compound that's completely neutral, you got to have a anion that is opposite to the +3, and that would be the 3 chlorides. So these are called counter ions. Just like if you had a regular salt, let's say we had a magnesium chloride. This would be the positive cation, and this would be the counter ion, so that this whole thing is neutral. Here, that whole thing is neutral. This would be the cation. That would be the positive charge species. And then what's outside the bracket are the counter ions. Okay, so the key here is that the ammonia is within the coordination sphere. The chlorides are outside the coordination sphere because the chlorides are not bonded directly to the metal, but they are attracted to the cation through electrostatic Coulombic interaction. Okay, so that know the difference between a counter ion and a ligand that's within the coordination sphere. So coordinated atoms are those elements that are directly bonded to each other and are contained in the coordination sphere or somehow connected through bonds to the transition metals. Counter ions are ions that are denoted outside the bracket, are not part of the coordination sphere, but are necessary so that the whole chemical is neutral. Okay, the counter ions are only necessary so that you have a neutral species. So that basically tells you the coordination compounds behave like electrolytes. When you dissolve this in water, it separates to its cation and anion, but the cation in this case is much more complicated. It's this whole thing that stays intact. It doesn't fall apart. And then you have the chloride as the negative anion. Okay, the complex ions behave like a polyatomic ion. And that is the ligand and the central metal ions remain attached. They don't break apart. So coordination number just tells you how many ligands. Let me rephrase that. Coordination number has to do with how many bonds a transition metal contains. So if you look at this transition metals, you can see that there are 6 bonds coming out of that. So we have a coordination number of 6. Okay, don't make it harder than it is. It's not that difficult. If you take a look at this, which might be silver, you can see it has, even though this might be a multiple bond, you've got 2 regions of electron density, and it's basically shooting off to 2 regions. So it has a coordination number of 2. Okay, if you take a look at this right here, this has a coordination number, this cobalt right here, just like if these were ethylene diamines. Okay, ethylene diamine is this chemical. For those of you in lab, you know what I am talking about. For those of you who haven't had lab, you guys will learn about it in this portion. This is ethylene diamine. It is a ligand, but the ethylene diamine can bind the metal. One ligand can bind the metals with 2 bonds. So even though you have 3 ligands here, 1, 2, 3, the coordination number towards that metal is still 6. because if you look at how many bonds that metal contains, it's got 6. So coordination number has to be, from the point of view of the metal, ligand number has to do with the point of view of the ligands, how many ligands there are, how many clusters of atoms there are bonded to the central atom, the transition metal. So the ligand number is 3, the coordination number is 6. They can be different. So chemicals that have a coordination number of 2 are generally linear. Chemicals with a coordination number of 4 can be one of 2 shapes. They could be tetrahedral, that's it right there, or square planar. And tetrahedrals are generally for D10, which means that there are 10 electrons in the d orbital. And square planars are generally for D8, which means that there are 8 electrons in the d orbital. Then you have trigonal bipyramidal and square planar. That would be for coordination number 5. These are sort of rare in the discussion that we are going to be talking about, but they still exist. And then the most common that we will see is the octahedral. The 2 most common geometry that we are going to be seeing in this discussion is the octahedral and the tetrahedral geometry. Okay. So again, this is a review. Linear, these are examples. Square planar, it's like a square. It's all in one plane. The plane is that right there. And these are examples of those compounds that contain square planar geometry. Tetrahedral, that's the geometry. These are examples. Octahedral. Let me do an example real quick, because I want to make sure that you guys are able to count electrons. That's manganese tetrachloride. So it's Mn, and there's 4 chlorides, Cl, 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 Cl. Now, the question is, what is the oxidation state of the manganese? And if you know the oxidation state of the manganese, how many electrons in the d orbital? First of all, this whole thing is -2. So the sum of the charges has to be equal to -2. Okay? Each of these chlorides are -1. That means in order for the sum equal to -2, the manganese has to be +2. And if you look in the periodic table, which I could go back to, okay, let me get out of here and find a periodic table real quick. You can see that the manganese is here. We know that it's a +2. 1, 2, 3, 4, 5, 6, 7. 7 minus 2, it's a D5. For that particular example, that manganese that I was talking to you guys about right here. Yeah, continue with my slideshow. This right here, that manganese is a D5. Just so that you know how to count electrons. Okay, so that was an example. So you should be able to do that based on the formula. You should be able to figure out what the oxidation state of the transition metal happens to be. And you should be able to tell me how many electrons in the d orbital. Here's another compound that's octahedral. Okay, it looks very complicated, but if you look around that central atom right there, you will see that around that, it has 6 bonds, and it's arranged in an octahedral type of style. Even though out here, it's confusing, if you look at the central atom, the geometry around that central atom is octahedral. That's why we cite that that's an octahedral geometry. For those of you who did experiment number 6 in lab, those chemicals that you synthesized, they were all octahedral, okay? They were all octahedral. So, uh, a review again. Coordination number has to do with, in terms of view of the metal, how many bonds the metal has, and it's going to be influenced by the size of the metal and the size of the ligand. So, small metals with large ligands can only accommodate a few of the ligands because there's not a lot of space out there. So they tend to have low coordination number, something like 2 or 4, versus those in which you have a large metal, you have a large metal and small ligands, then you can accommodate more than 4 ligands. You can accommodate more ligands around them, and so they tend to have high coordination number. So let that be your guide as to whether you would have, if you're given a transition metal and a ligand, you should let that be your guide as to what the geometry or what the coordination number should be, whether it be um, low coordination number and therefore be tetrahedral or square planar, or high coordination number and therefore become an octahedral. When you have a coordination number 6, there's only one geometry that we need to know, and that's octahedral. So let's take a look at the ligands real quick. The ligands are those group of elements that are binding to the metal, and these are going to have lone pairs. All these are ligands right here because they have lone pairs that can bind to the metal. Polydentate ligands, just like ethylene diamine. Okay, I already drew you this structure. And what we will do a lot of times is we're going to do a shorthand notation. So whereas this chemical is this in terms of its formula and its structural arrangement, this nitrogen has 2 hydrogens connected to a carbon. This carbon has 4 bonds. 2 of these goes to a hydrogen, and then the other 2 goes to a nitrogen and a carbon. What we tend to do is do a shortcut. We don't write the hydrogen because the hydrogens are implied, and so we end up doing this. And we know that the hydrogens are there because we know that nitrogen and carbon needs to have 4 bonds. And what we can do even further is we know that in organic chemistry, there's always a carbon in the main chain, in the backbone. So we can just do this, where this now represents carbon and the hydrogens are implied. And then, yeah, you might think it's ridiculous, but it saves a lot of time. We do this a lot of times. We don't even draw the fact that there are 2 carbons in there, and then we just say that that is the representation of ethylene diamine, En. Okay, so you got to be able to, and if you go into organic chemistry, because you want to go into med school, you got to understand all these shorthand versions of how we represent atoms or molecules, because they're going to start doing it on you, and it's your responsibility to know what they mean. So we go from a very sophisticated structure like that, which takes a long time to draw, to something that looks like this, which takes less time to draw, to something like this, which takes even less time to draw, to something even like that, where it's really quick. Okay, so if you go to organic chemistry, they're going to do a lot of abbreviations on you. It's up to you to know what those abbreviations are in terms of the structure. So just as a little background. So polydentate ligands are ligands that can chelate. Chelate comes from the term bite or grab or claw. So these chemicals can claw to the metal in more than one site, 2 or more. Poly means many. Dentate means bite, and so they have more than one bite. Okay, and they are ligands because they have lone pairs to donate.
Professor,
Yes.
would ethylene diamine be an example of a polydentate?
Yes, exactly. Ethylene diamine is a nice example of a polydentate ligand. To be specific, it's what we call a bidentate ligand. And the reason why it's called a bidentate ligand is because it's got two sites to bind. Okay, we have something called tridentate, uh, and then there's polydentate. But poly is just a generic term meaning two or more. If you want to be specific for ethylene diamine, uh, that you guys did in experiment number 6, it is a polydentate ligand. More specifically, it's a bidentate ligand. And you see that a lot. You see that a lot in uh, nature. Okay, EDTA. We work with EDTA when, for those of you in lab, when we did the equilibrium experiment, that's a polydentate ligand. I'll show you that structure momentarily. So these are all examples of polydentate ligands. Here are some of the ligands. Notice they all have what they have in common. Uh, they all have lone pairs to donate. So these guys up here are actually monodentate. They're just plain ligands because they only have one site to bind. Even a chemical like cyanide, okay? Even though these guys have two places to bind, they could bind through the carbon or the nitrogen. They can't wrap around. They have to have the flexibility to wrap around, at least make a square in order to be a polydentate. So a structure like cyanide, even though they can bind through the carbon or the nitrogen, is not a bidentate ligand because it can't wrap, it can't be, it's not flexible enough to bind the same metal at the carbon and nitrogen. Okay, but other elements or other compounds are available to do that. And let me show you that shortly here. So these are neutral ligands. Water is not called water, it's called aqua. Ammonia is not called ammonia, it's called amine. NO is nitrosyl. CO is not called carbon monoxide, it's called carbonyl. These are the names of the ligands. Okay, and then any ligand that is charged, like the fluorine with an extra electrons, or the hydroxyl OH, or the cyano CN minus, they always end in an O suffix. Okay, fluoro, chloro, bromo, iodo, hydroxyl, cyano. So generally, you know it's an anionic ligand because they end in an O in their name. So here are more examples. Pay attention to oxalato. That's the oxalate ion, but as a ligand, it's called oxalato. Oxalato. Notice it has -2. Uh, Thiocyanate, it's thiocyanato. Thiocyanato. Okay. So these are just names of the ligands, and if you have a good list, then you're set. These are polydentate ligands, and notice that they have two lone pairs that can somehow wrap themselves around so that they can form a ring when it binds to the metal. So these are polydentate ligands. And this right here is this ligand right here. This is the ligand right here. Let me show you what the structure of this chemical right here. You see this right here? That looks like an ethylene diamine. So it's called ethylene diamine because the inside is an ethylene diamine. You see this right here? Well, that is nothing more than acetic acid. This is acetic acid. When you remove one of the hydrogens, then that's called an acetate ion. Okay, so this chemical right here is acetate. and there's four of them. So what do we call this compound? We call this compound ethylene diamine tetra, meaning four, acetate, better known as EDTA. Okay? So if you remember the building blocks of EDTA, ethylene diamine tetraacetate, it's not a difficult structure to draw. Just draw the ethylene diamine, and then where there's two hydrogens out here in the nitrogen, where there are generally two hydrogens, you attach the acetate group. And the magical thing about this particular ligand is that there's lone pairs here, lone pairs here, lone pairs here. Okay, let me circle these. Lone pairs here, lone pairs here, lone pairs here. And so what they can do is they could wrap, all these lone pairs can wrap a metal in that configuration. And it's one ligand with a coordination number 6. That's why ethylene diamine is such a magical ligand, because it basically sequesters the metal. And so it's a great antidote in terms of preserving chemicals, because then that metal can't be oxidized and you don't have free radicals. More importantly, if you ever get heavy metal poisoning, let's say you have a child and somehow they start eating lead through some of the paint or something, or they ingest some sort of heavy metal, one of the antidotes that comes from the poison control kit is EDTA. And that's because EDTA will sout out that metal and bind it, and then it will be water soluble so that the body can release it through the urine. Okay. Otherwise, that metal just gets embedded in the lipids of the body, okay, the fat cells of the body, and then it sort of gets released over time. And of course, we all know about lead poisoning, okay? It messes up the central nervous system. But EDTA, because it's such a great ligand, it's such a great sequestering agent, is used as an antidote for heavy metal poisoning. So here is a list of more anions that could be used as a ligand, okay? It's just a compiled list. And then chelating, remember, is the idea that one ligand can bind the metal in more than two sites, or two or more sites. That's what chelate means. It means it's many tooth, a polydentate, or a chelating agent is one that can bind the metal. One ligand binds the metal in two or more sites. They're called sequestering agent because they sort of isolate the metal. So it's sequestering. And ethylene diamine certainly is an example of that. Again, we use EDTA as our classic example of one ligand with a 6 coordination number for the metal. And you see this a lot in nature, these polydentate ligands. You see it in hemoglobin. In hemoglobin, what you see is the heme site. This is one chemical with binding the iron, and iron is so important because it's the iron that is responsible for holding on to the oxygen in the lungs and delivering it to our cells when it gets transported through our blood. And there are 4 heme groups in hemoglobin that will allow you to do that. But that, again, is a polydentate ligand, the heme site in hemoglobin. Then you also have vitamin B12. And if you take a look at this example right here, you see that this is the metal, the cobalt, and it's got this complex array that is just surrounding it. And then you have zinc fingers. And here it's a tetrahedral geometry around the zinc. And then you also have ferrochrome, oxymyoglobin, and chlorophyll. Those are all examples of polydentate ligands, and they bind to one central transition metal. So it's very important for life, and we study it. Okay, complexing um, effect. The reason why metals want to complex versus say just a regular monodentate ligand is because of this right here. We have, let's take a look at nickel. It's got 6 waters, and we're going to replace the 6 waters with ammonia. And when that happens, then the waters come off, the ammonia comes in, or the amine comes in, and that has a Kf of 4 times 10 to the 8th. Very efficient reaction. The equilibrium constant is much, much greater than 1. But look at this right here, okay? If you take a look at that reaction right there, the water is now replaced by ethylene diamine. And in the process of doing that, we go from 6, 7, 8, 9, 9. Sorry, let me recount that. Okay, we've got 1 here, and we've got 3 here. So that's a total of 4. And then our product has 1 and 6. That's a total of 7. So you see how entropy increases in that reaction? Well, that's why chelating reactions are very efficient, because when we go from reagents of 4 to products of 7, it has a big entropy effect. And look what happens to the equilibrium constant, the formation constant. It goes from 4 times 10 to the 8th to 2 times 10 to the 18th. That's very, very favorable in terms of entropy driven. And so those things are entropy driven. So I'm going to switch gears on you now, because this is an important topic that we need to cover. That's the nomenclature. How do you name these things? Well, there are certain rules, and hopefully you guys remember your rules from general chemistry as to how to name a salt, something like this right here. If you got, let's say you got iron, and you've got sulfate, and let's say this is a +3 and this is a -2, then the formula we would have is Fe2SO4 3 times, okay? And this guy would be called iron 2 sulfate. The iron, sorry, it's iron 3. The iron 3 is not because you have 2 irons here, but it's because it's a charge of +3. Whatever the charge of the transition metal is, you always put in Roman numerals. And so that's the same idea when you name these things. You name the cation first, followed by the anion. Okay? You name within the cation the ligands, and then the metal, followed by the Roman numeral, and then the anions. So that's the general structure of naming these things. So let's look at the exact rules. Complex. Within a complex ions, the ligands are named in alphabetical order before the metal. So if you take a look at this right here, the ligand is amine, and there are 5 of them. So we have to use penta to indicate 5. Amine, don't put AA, just put pen. Yeah, you do put AA. Pentaamine, that takes care of the NH3 5 times. And then it's cobalt. And then if you look at this right here, there's a chloride that's a -1, and there's 2 bromines that are -1 apiece. So in order for that whole thing to be neutral, that has to be a cobalt 3. Okay, that has to be a cobalt 3. I forgot to put in here that there's also chlorine in our coordination sphere. So I need to do this. I need to put in here chloro, cobalt 3, and then bromide. Okay, so this name would be pentamine chlorocobalt 3 and then bromide. Don't put dibromide here, because you should know from here that the cobalt is +3, the chlorine is a -1, so that whole thing is +2, and so all you need is 2 bromines as a counter ion. Okay, so you don't need to put dibromo. You can figure it out based on the elements or the ions, that are that are in the name. Cobalt's +3 because you indicated here the chlorides are always -1 and there's only one chloride. Otherwise you would have put di here or tri if there was more than one. Don't put mono, just put chloro and then bromide. Okay. When it's more than one, you put di, tri, or tetra. But if there's only one, just put chloro. Don't put mono. That shouldn't be put in there. So that's the name of the compound that we have right here. Okay. That right there would be this compound right here would be pentaamine chloro cobalt 3 bromide. And again, you're using the prefix to indicate how many ligands you have. If the ligand already has a number in it, like ethylene diamine, you see how ethylene diamine already has a di in it? So if there are 2 ethylene diamine, you have to use the secondary prefix from the Greek and say bis ethylene diamine. I know it's a lot of information now, but once you get the hang of it, it will be pretty straightforward. Okay, so let's take a look at this example real quick. This right here, this ligand is called bipyridine. Bipyridine is this chemical right here. It's got 2 lone pairs right here. This is called a pyridine ring. Okay, the circle means there are alternating double bonds, but this is bipyridine. It's a bidentate ligand, and there's 3 of them. So when you name this guy, you don't say tri-bipyridine, you say tris, because bipyridine already has a bi within the name of the ligand. So you say tris, and then parentheses bipyridine, and that's an iridium 3 compound. If the complex is an anion, then its name ends with the suffix ate. Okay, that's the thing. So if the complex is an anion, let's say that this right here, this is a cation actually, because that's a +3 and that's a -1. But if it were an anion like FeCN6, and let's say that iron is +3, so the cyanides are -1 apiece, that's a -6. So this right here would be a -3 anion. Then we need to have a suffix of ate in the name. And I'll show you that example shortly here. So that's the rules for naming. So let's take a look at that. For formulas, right, the cation is written before the anion. Charge of the cation is R balanced by the charge of the anion. It has to be like electrically neutral, or if it's charged, then the net charge of the elements within the compound have to equal to the overall charge. For the complex ion, neutral ligands are written before the anionic ligands. So when you're writing the formula, okay, you write the neutral and then the anions. Negative charge and the whole ions are placed in brackets. For naming, the cation is named before the anion. Within the complex ion, the ligands are named in alphabetical order. Neutral ligands generally have the molecular name. Okay. Anionic ligands drop the IDE and add O. We saw that already. Numerical prefix denote the number of a particular ligand. Okay. So rather than explain these rules, I want to show you an example that way you can see how these rules are applied. Okay. Oxidation state of the metal is in Roman numeral So let's take a look at an example. Say we have this compound right here. So we want to write the formula, or we have the formula and we want to name it. So this is called the ethylene diamine, that's called fluorine. Ethylene diamine is E, fluorine is F. E comes before F. So in alphabetical order, ethylene, and there's two, so it's bis ethylene diamine, 2-fluorine difluoro chromium. What is the charge of the chromium? Well, let's take a look. Nitrate is -1. Fluorines are -1 apiece. Ethylene are neutral. So the chromium, for all this to be neutral, has to be a +3. Okay. The overall charge has to be 0. Fluorines are -1. There's 2 of them. Nitrates are -1. There's 1 of them. So the chromium have to be +3. So let's take a look at it. Bis ethylene diamine, meaning 2 ethylene diamines. Difluoro, 2 fluorines. Chromium, 3 nitrate. Okay, let's take a look at the second one. Now our transition metal is an anion, so it has to end in an ATE. This is potassium. We named the cation first. Here we have amine and we have oxalato. Okay, and there's 2, so there's dioxalato. There's 2 here, and there's 2 amines, so there's diamine. A comes before O, so we would name diamine dioxalato, and then the metal is cobalt. And then if we look at the charge, let me erase this so that you guys can see what I'm doing here. If you look at the charge, the potassium's +1, the oxalic acid is -2, but there's 2 of them, so that's -4. So -4 and a +1, the cobalt has to be a +3. Okay, cobalt has to be a +3 for this whole thing to be neutral. Remember that ammonia is neutral. The amine ligand is a neutral ligand. And how do you know that? It doesn't end in an O, like oxalato. So let's take a look at the name here. Let's take a look at the name here. So the name would be, potassium, cation first. Diamine, A before O. Dioxalato. Cobaltate, that's where you put the ATE ending, because it's an anion, 3. So there's a special rule in naming these things. This last one would be potassium, and don't put tripotassium, it's just potassium. How do I know? Because I know that this whole thing is a -3. Okay, so potassium, and then cyanide is negative. Cyanides are -1, and there's 4 of them, so that's a -4. That's a +3. The gold is going to be a +1, and gold is aurate. Okay, that's the Greek name for gold, aurium. So it'll be aurate. So let's take a look at that name real quick. Potassium, tetracyano, because there's 4. Aurate, because it's an anion, 1. Okay, let me do the last example here since we're running out of time. These are the different ways of naming these metals. Let's take a look at the formulas from the name. Remember, when you write the formula, it has to be neutral before anionic. So here we have an amine, that would be NH3, and hexamine, and then nitrates NO3. So the formula would be chromium, Cr, that's a +3. There's 6 ammonia, NH3, okay? And then there's going to be a nitrate, NO3. But remember that chromium has got to be a +3. How do you know that? It's right here in the name. So you need 3 nitrates. You need 3 nitrates to balance that out. So we have hexaamine chromium 3 nitrates in order to balance out the +3 of chromium. And remember, don't look for the charge in the periodic table. It's got to be given to you in the name. It's got to be given to you in the name. Here, dichlorobisethylene diamine. So there's 2 chlorides here, and there's an ethylene diamine, and then there's a platinum, that's 4. Chlorines are -1 apiece, and there's 2 of these. So that means there's 2 bromides, because ethylene diamines are neutral ligands. So that's what we see. Platinum, ethylene, diamine 2, chlorides 2. That's going to be in bracket because that's your cation. And then you have 2 bromides. It's got to be electrically neutral. Finally, the last one here, we have bisethylene diamine. So there's 2 ethylene diamine. That's this. There's a zinc that's +2. And then there's a counter ion here. It's a complicated one. It's got mercury, and the mercury has 4 iodines. And if this is +2, and the iodines are -1 apiece, so that's -4, then that mercury has got to be +2 because the whole thing has got to be neutral. Yes, En would be acceptable rather than, because that's the common abbreviation for ethylene diamine. But one common mistake that a lot of students will do, let me show you this common mistake, which you do not want to do, okay? Don't do this. Let me erase this. Let's say that I'm going to draw this as its structure. Let's say I have zinc. Don't do this. That's not acceptable for ethylene diamine. What you need to do is you need to draw out the nitrogen that is bonded to the zinc. What you need to do is not do that, but do this. And then just say N equals ethylene diamine. Do not draw ethylene diamine this way. That's unacceptable. Okay, so let's do the last one. That's bisethylene diamine zinc 2 tetraiodo mercurate 2. That's the name of that. So what you need to do is you need to practice this, and I believe there are a bunch of homework problems that have you practicing this. For those of you who have lab, you guys have a bunch of nomenclature in coordination chemistry, okay? And you just need to practice. So that's the fundamentals of coordination chemistry.